start off, these are notes for Chapter 5, and the topic of the whole chapter is the periodic law. You kind of got the first chunk of the notes in the little video that was sort of background. And I kicked that out to a kind of flipped position because that used to be included in the state standards, and they de-emphasized that part. So we're going to talk about the part that the state considers more important, and also I actually think the part that will help you more as you go on in chemistry, because a lot of you are going to end up taking chemistry in the future. Okay, so one term, and like I said, we kind of shift the background stuff out to a position where you take care of it on your own. But this concept is key to understanding everything that happens in chemistry. And what's so cool about the periodic table, you've seen the periodic table before. You looked at it in physical science. You know metals and nonmetals and transition metals. There is so much more information packed into that periodic table than you even have any idea. It's astounding how much stuff. It's like 20 secret codes written all on top of one another, and if you know what you're looking for, you can just keep digging and keep finding, oh, that's there too, and you keep digging, oh, wow, that's in there too. There are just all these layers of information, and you've kind of scratched the surface. You've gotten the first couple. But it all comes back to periodicity, which is this tendency to recur at regular intervals or periodic intervals. We could say that school starts periodically, same time, every day, 5 days a week on a repeating schedule. And periodicity in the table happens in both atomic number and in chemical characteristics. So I'm going to pop in the periodic. So we'll talk a little bit more about the atomic number piece. But in terms of chemical characteristics, you know that chemical characteristics tend to be grouped by what? By group or by period. So the rows that go across or the columns that go up and down. Chemical characteristics are similar within. Okay, so chemical characteristics tend to recur in those groups. So each group tends to have related chemical characteristics. So before we start talking any more about electron arrangement, I want to make sure that we've got our terminology straight. So when we say 1, 2, 3, 5, 7, that's main energy level. That's that N equals. A subshell would be like the 3s or the 2p, the 4d, and an individual orbital would be, 1s, 2px, 3d3. Those are individual orbitals. This is important because the periodic table actually has a whole bunch of information about electron configuration hidden in it. Okay, so electron configuration on the periodic table. I'm actually going to read this to you word for word, which I normally think is stupid, but I want you to hear how complicated this sounds. Groups run vertically, periods run horizontally. Great, we know that. Length of periods determined by the number of electrons that can occupy the sublevels being filled. Period 1 fills 1s, which holds 2 electron, and there are 2 elements. Period 2 begins filling 2s. Is that crystal clear? Is that completely incomprehensible? Usually it's closer to completely incomprehensible than crystal clear. So what I want you to do is look at that periodic table that we've been pulling out from time to time, the good old Van Brainer. Whoops. Let me pop a Van Brainer in here. And I would like you, I'm going to move this down towards the bottom of my screen. I would like you to write the electron configuration notation for hydrogen. Hydrogen has 1 electron. Its electron configuration is... okay, well that was easy. Okay, so we've got hydrogen's notation. And actually the image that I've got doesn't have the 2 hydrogens. Your paper copy does. So now I want you to write helium's electron configuration notation. Let me see if I can make that darker. So we've got helium, we've got hydrogen, we've got helium. They're the entire first period of the periodic table. We kind of hinted at this in the last chapter, but the highest main occupied energy level is the same as the period. So everything that's in the first period, its highest main occupied energy level is N equals 1. Well, look at that. There are only 2 elements in the first period. That's stupid. How many electrons can we fit on the first main energy level? 2. Huh. Coincidence? So, I'd like you to write the electron configuration notation for lithium. Yay, lithium. Hydrogen, helium, lithium, and beryllium. Go ahead and write out the notations for boron, carbon, nitrogen, oxygen, fluorine, and neon, if you would be so kind. Okay, so we've got 1s1, 2s, or 1s2, 2s1, 1s2, 2s2. Then we've got 1s2, 2s2, 2p1, 1s2, 2s2, 2p2, 2p3, 2p4, 2p5, 2p6. Huh. So, what do you notice about the second period? What main energy level is it filling? 2. We're filling 2s1, 2s2. Here we start filling in 2p. And we get all the way over to 2p6 by the time we get to neon. Huh. How many elements are there in the second period? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. 8 elements in the second period. How many electrons can you hold on the second main energy level? 8. That's so weird. What about sodium? Let's write the electron configuration notation for sodium, but let's make it easy on ourselves. We have a shortcut for writing electron configurations. What's our shortcut? Noble gas. So we can do this using noble gas notation, and we see that it's neon plus 3s1. Okay, so go ahead and write the noble gas notation for magnesium. That would be this one right here, 12 electrons. We have neon 3s2. If you had to, well, you know what subshell is going to fill next. What subshell is going to fill next after 3s? 3p. Guess what we're filling over here? 3p's. So in the third period, what you're filling is 3s and 3p. Huh. How many electrons can be held between 3s and 3p? 8. Guess how many elements there are in the third period? 8. Weird. Just flat out weird. So, what we're looking at is 2 things. The length of those periods really is governed by how many electrons we can fit in the subshells that are being filled. And the highest main energy level occupied is always the same as the period. So if we look back here, highest main occupied is 1. Highest main occupied is 2. Highest main occupied is 3. Guess what the highest main occupied in the next period down is? 4. And we kind of hinted at that in the last chapter. So, let's practice. And I will ask you these on, on a test or a quiz. What's the highest main occupied energy level for an element in the 5th period? Those are easy gimmies. That'd be 5. So, what's the highest main occupied energy level for nitrogen? Look on your periodic table. So that's pretty easy. I can pick out any element on the periodic table and ask you what's the highest main occupied energy level. You're going to know it's the same as the period. Now, here's where the colored pencils are going to come in. Let's actually go back to here. And let me get rid of my little blue lines here. What do you notice about helium, lithium, and sodium's electron configurations? Anything. So note something and then talk with somebody near you about it. Discuss. Talk amongst yourselves. So here's somebody who's noticed that they all seem to end with S1. Go ahead and write the electron configuration for potassium. If what you're seeing is a pattern, what would you expect potassium's configuration to end with? 4s1. So it would be the noble gas, and what's the noble gas behind potassium? Argon 4s1. Could it really be that easy? Could it? Yes, it actually could. It could, and it is. Every single element in the first period, in the first group, so in group 1, and that is these guys, is going to end with a something S1. Something S1. And that something is always going to be the what? The main energy level. So these guys all end with N, because N is main energy level, S1. Cool. We can now write electron configurations using noble gas notation for these things in about 3.5 seconds without ever counting an electron. Nice! I hated counting electrons. I hate writing stupid orbitals. Ugh. Well, what about group 2? So let's get rid of, whoops, let's reinstate that, but let's get rid of this. So these guys are all NS1. What do you think is happening in group 2? NS2! Amazing. Because you'll notice here we have 2s2, 3s2. Guess what the next one down ends with? It's argon NS3. Well, it's argon 4s2. Yeah, I think I said that all screwy. But yeah, it's the same thing, a noble gas, and then you're filling in the 4s2. Huh. Cool. Well, we're going to skip back up to there, to aluminum. Hello, aluminum, my old friend. I've come to bend you up again because you are highly malleable. Anyway, I know, don't quit my day job. So, aluminum, write its noble gas notation. Okay, so neon, 3s2, 3p1. Could you have predicted that that would end with a p1? Why, yes, you could have. Could you predict, so this is always going to end with NS2, NP1. Guess what the next ones end with? NS2, NP2. You people are astoundingly clever. We just keep adding one electron every time we move over. If you had to bet money, or like your puppy, or your sibling, what would you bet the next group's configurations always end with? NP3! Give that man a puppy. Yes. It would make a fantastic game show. We could award puppies. Okay, now, what you've just seen is the basis for how we're going to use colored pencils. The periodic table can be coded into blocks. And what we refer to as the blocks are all based on what sublevels are being filled. So there's an S block. You want to guess which groups comprise the S block? Group 1 and Group 2. So if you have your periodic table, I would invite you, and I will pop in a periodic table here. I would invite you to choose some color, it can be any color you want, and color groups 1 and 2 on your periodic table, and make yourself a little key somewhere that says, hey, this color, this is the S block. Remember that when we did boron and carbon and nitrogen and oxygen and phosphorus and down to aluminum, they were all filling where? P's. So this whole chunk here, straight down, is the P block. So pick a color, make something, some little key for yourself that says, ooh, that's the P block. So on the periodic table that I gave you guys, there's another hydrogen here. I very often have people cross that out. We're going to talk about why there are 2 hydrogens on there, probably talk about it today actually. So you've got your P block elements. You know, the question being, should I color these blank spaces? Yeah, because if there are elements there that are, and these are all going to be human created if they show up, they're going to be filling in the P's. Really high P's, but they're still going to be filling in the P's. So let's go back to our periodic table for a moment, and let's do the electron configuration for scandium. It's atomic number 21, and you know that it must have argon 4s2. Now the question is, what subshell starts filling after 4s? 3d. So this is going to have 4s2, 3d1. Guess what this one's going to have? Argon plus 4s2, 3d2. Hey, you people are clever critters. I keep saying that. So these, in general, finish with NS2 N minus 1 D1. Because remember that D level is always one level back. And so this entire group is going to have 1 electron in a D subshell. This entire group finishes with NS2 N minus 1 D2. And you see the pattern. So everything in this middle area, well, how many orbitals are there in a D subshell? 5, so we can hold 10 electrons. Let's see, how many elements can we fit in here? 1, 2, 3, 4. Does anybody have a prediction? 10! 5, 6, 7, 8, 9, 10! It's crazy. So by the time we get over to here, we've got NS2, N minus 1, D10. Hard to draw. So guess what? We call this middle section. Yeah, it's the D block. So pick yourself a pretty color. Label appropriately. That's the D block. Okay, so we've colored everything on the periodic table, right? What have we missed? The weirdos down at the bottom. So where the heck do they fit in? I want to give you another periodic table. This is called a long-form periodic table. Once you have seen it this way, it will never make sense again the other way. I never saw this in high school. I never saw this in college. And subsequently, it never made sense to me. I love this thing. It makes total and perfect sense. So here we were filling in the 4 S's, and then we went to the 3 D's, right? Yeah. So here we're filling in the 5 S's, and then we go to the 4 D's. And from 4, so this is filling 4D. What fills after 4D? I should color code these with my blocks. 5P. Yeah, let me make these the right colors. Come on, Moser, you went to all the trouble to color code stuff. Whoops. Five S, 4D, 5P. What fills after 5P? What is it? After 5P? 1S, 2S, 3S, 4S, 5S, 6S, 2P, 3P, 4P, 5P. Gotta shrink this. Let me throw 7S in there for good measure. And then 3D, 4D, 5D, 6D. I'll throw 7P in there for good measure. And 4F, 5F, 6F. Let's throw 7D in there for good measure. 1, 2, 3. Oops. Well, I'm making those really messy. Maybe I should just make that a pencil. Three D, 4P, 5S, 4D, 5P. What fills next? 5P, then what? 6S. 6S. Now, what fills after 6S? 4F. That makes sense now? Okay. And I'm going to pick a really crazy, wild, obnoxious color for our last little group here. Oops. So here we start filling 4F. And how many orbitals do we have in an F subshell? We had 1, 3, 5, we have 7. 14 electrons. How many spaces do you think there are? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14! Who could have predicted this? Me. I could have predicted it. We're filling an F subshell now. So we now have 14 elements. That F block is 14 elements wide. After 4F, looking at this chart, what fills next? 5D, and lo and behold, guess what? We're back in the D block. Cool! What fills after 5D? Why, our friend, 6P, and look at that. We're in the P block. What fills after 6P? You don't even have to look at this now, because you know that after 6P we roll right back to what block? S block. And it's going to be 7S. And then after 7S, you don't even have to look at the orbital filling diagram anymore, because what's going to fill after 7S? Well, we're in which block? The F block. And we're always 2 back, so this is going to be 5F. What fills after 5F? Once again, you no longer even have to look at the subshell filling chart, because you know that from the F block we go right straight into the D block, 6D. After 6D, what's going to fill? 7P. I won't say that it makes the subshell filling diagram obsolete, but it comes pretty close, because you can now look at anything and say, oh, well, this is filling in the blah, blah, blah. This is going to be filling in the 4S. You don't have to count anything. You don't have to do any kind of orbital notations, because you know your blocks. So let's go ahead and we'll finish coloring in our F block. And make yourself whatever pretty color you like for the F block. I think that really the subshell block information on this is the most useful, because what governs how chemicals behave, what governs how elements behave? Their electron configuration, and specifically what blocks they're filling in and sort of what their goal is. And, we always say everything wants to be like a noble gas. This kind of gives you a clue as to what they need to do to be like a noble gas. So there's the sort of traditional sub-level block view. But again, like I said, I don't think it makes any sense until you see, for the very first time, the long form view. And it's such a great, easy cheat. So if I ask you a question on a test and I say, what subshell is this element filling in? I expect not only the energy level, I expect, 3D, 4S, 2P, because you can get all that information. What gives you the number? The period. What gives you the subshell? The block. So the blocks are great because we can just say a lot of, oh, well, it's a D block. It acts like a D block. We can classify it that way. There are 2 that are kind of weirdos. So helium and hydrogen, why are they called the original elements? Why would helium and hydrogen be called the original? Where do we make atoms? Whoa, make atoms? You can't do that. Oh, well, we can make everything out of hydrogen. And as a matter of fact, at the moment of the Big Bang, which is, from our vantage point in time and space, the observable beginnings of our universe, it's the point at which all matter in the universe appears to have been compressed into one tiny area, and from there it outwardly expands. Okay, that's from our vantage point. There may be more to it, but from what we can observe, that's what the evidence points to. At the moment of the Big Bang, there aren't even hydrogen atoms. For a little while, in what they call Planck time, there aren't even protons and neutrons and electrons. There are subatomic particles. So those have to coalesce first, and then you start seeing hydrogen. Well, where's someplace that you can see with your naked eye that helium is being created from hydrogen? Yes, in the sun. Good. How'd you get that? In the sun. Our sun is a giant plasma ball where hydrogen atoms are being smashed together to make helium. And in fact, in our universe, hydrogen and helium would have been the first 2 elements, because you smash hydrogens together, you get heliums. So they're a little weird. Hydrogen has a 1s configuration. Based on electron configuration, it belongs in group 1, because it ends with an S1. It doesn't act like a group 1 element, because it wants to get to be like the nearest noble gas, which means gaining 1 electron. Hydrogen actually acts more like a p block element. Helium acts like a noble gas, but it isn't filling up a p. By electron configuration alone, helium would be here, but it doesn't act like a group 2 element. It acts like a noble gas. So we place it with the noble gases. They're kind of weird because they only have electrons on that first level. So that's why your periodic table that I gave you shows hydrogen in group 17. Based on electron configuration alone, it's clearly group 1. But it acts like a group 17 element. So some periodic tables choose to show it in both places. That's the only reason that we do that. Okay, we're going to talk a little bit about each of the blocks, and then I'll cut you loose to do homework. So the S block are highly reactive. They're so reactive we don't find them on their own in nature. This is your friend who cannot go to the bathroom by themselves. Can't stand to be alone. This part's important. The number of electrons in the highest occupied energy level equals group number. You have used this before, you just didn't call it that. You called them valence electrons. The number of electrons in the highest occupied energy level. That's your valence electrons. And in the S block, it's equal to the group number. So if I have a group 1 element, how many valence electrons does it have? 1. If I have a group 2 element, how many valence electrons does it have? 2. S block is super easy. This is important because as we go, you'll need to be able to go on the fly. Oh, it's got 1 valence electron. Oh, that forms a +1 ion. And you'll be very good at that. Group 1 are alkali metals, group 2 are alkali earth metals. Quite frankly, I'll be honest, I can never keep straight which is alkali and which is alkali earth. Does it matter? I know which group behaves which way. So I'm not going to fault you if you get those mixed up. But I expect you to know that group 1 tends to give up 1 electron, group 2 tends to give up 2 electrons. And we'll talk more about that as we talk about bonding. Oh, the p block. So we call the S block and the P block the main group elements, and they're the sort of easy, predictable ones. You always know what they're going to do. They don't do anything weird. Their number of valence electrons is their group number minus 10. So number of electrons in the highest main occupied energy level is equal to their group number minus 10. So if we pop in a periodic table here, this is group 13, 14, 15, 16, 17, and 18. How many valence electrons does something in group 15 have? Show of fingers. 5. How many valence electrons does something in group 13 have? Show of fingers. 3. Group 17? 7. Yeah. Group number minus 10. That's all it is. That's the number of valence electrons they have. How many valence electrons does group 18 have? 8. That's that magic number. We talk a lot about the octet rule, and we'll talk more about that as we move forward. Okay, the D blocks. The D block are the metals. These are the ones that are what you think of as metals. Groups 1 and 2, the S block, are also metals, but these are what we think of as sort of classical metals. They're called transition metals. And we start to get these weird overlaps, and that's where, either having your orbital subshell filling diagram, or your subshell filling diagram, or knowing your block arrangement really well helps. So we don't talk so much about valence electrons with D block. We do talk about which electrons participate in bonding. And in this case, it's sort of a last in, first out thing, which means most often it is D electrons, D orbital electrons that are participating in bonding. But the sum of the outer S and D is the group number. And if you think about going from group 18, doing noble gas notation, we add, 4s1, 4s2, 3d1, 3d2. That gives you the group number. The transition metals are a little bit special. All the things that you know about them, they're great conductors. They tend to be very hard. Lustrous means shiny. They reflect light. They are not as reactive as the alkali and alkali earth metals. They're not as reactive as the S block. They're like the calmer, older versions of the S block. There are some that actually don't even form compounds. Gold doesn't form compounds in nature. Silver will form compounds. You can get silver oxides, but just as often you can find veins of pure silver. You can also find veins of copper. Those are all things, they're not completely unreactive. You can oxidize copper or silver or anything else, but some of them don't. And there are a few of the transition metals that are actually used in the body. Does anybody know someone who has a metal bone replacement? I know somebody who's got a patch in his skull. He had a head injury in his 20s, and he's actually got he calls it a steel plate. In fact, it's more likely to be titanium because titanium's non-reactive. My grandfather, and this was in the 70s, had an industrial accident where his leg was crushed. The bone was just powdered, and they replaced it with a pin. They replaced it with and again, he would call it a steel pin. It was probably a palladium or titanium alloy, and very often people get titanium hips these days because they're not reactive. And your body is full of all sorts of interesting chemicals that would just love to react with something. Lots of salts, lots of reactive compounds. Okay, we'll just briefly talk about the F block, and then we'll be done for the day. So these are all things that are filling in the Fs. We only go up to 5F. The largest known elements are filling in 5F. They're called lanthanides and actinides. They are highly reactive. Lanthanides are very, very reactive to the point where they're not found sort of in the wild on their own. They're too reactive for that. And the actinides are actually all radioactive. They are large enough, they have large enough nuclei that they can't even hold themselves together. That said, we don't deal a whole lot with the lanthanides and actinides, but that is something you should know. Okay, I'll assign some homework problems, and we'll pick it up tomorrow.